Hello everyone and welcome back to the Doc Vile A-Level Chemistry Revision channel. This channel is all about getting you ready for your A-Level exams, and in this video we're going to focus on standard electrode potentials, which is all about the way that chemicals can either gain or lose electrons and how the flow of these electrons can generate an electrical current or a voltage. And we can use that in the principle of how batteries work, and that's what we're going to look at. It's quite a complex topic, so what we're going to do is take it back to first principles and try and understand what's going on here. So let's take an example that we hopefully are familiar with, the reaction between zinc and copper sulfate. Now, if you think back to GCSE chemistry, hopefully you remember that zinc is more reactive than copper. So if you have zinc and copper sulfate, CuSO4, and you mix them together in a beaker, then what would happen, because the zinc is more reactive, the solid zinc would displace the copper from the aqueous copper sulfate, and you would form solid copper and zinc sulfate, aqueous. And the reason this reaction happens is because the zinc is more reactive than copper. Now, what's going on here is two what we call half cells or half processes, half equations. And in the first one, the zinc solid is going to zinc 2 plus in the zinc sulfate. And it must be losing 2 electrons to do that. So zinc goes to zinc 2 plus and 2 electrons. And in the other process, the copper 2 plus, so the copper from the copper sulfate, is gaining those 2 electrons to form copper. And what I've not done very clearly here is actually illustrate that these processes are reversible reactions. So the zinc and the zinc 2 plus are in equilibrium, and the copper 2 plus and the copper are in equilibrium. But because the zinc is more reactive, this equilibrium prefers to sit onto the right hand side. In other words, it likes to lose its electrons, whereas the copper 2 plus prefers to gain 2 electrons. So the equilibrium lies towards the copper. Now, this is all happening at the moment in one beaker, but what if we could separate these two processes into the two half equations and keep them separate? Well, let's have a look at that on the next slide, the practical setup for this. So firstly, imagine you've got a beaker, and into your beaker you put some solution, and that solution contains the zinc 2 plus ions, and you dip into that a solid zinc rod. So that's your first beaker. Then you get a second beaker, same kind of thing, but you put a copper rod instead of a zinc rod. So this is now made of solid copper. And in here you'd have zinc, what am I trying to say? It's not zinc, it's copper 2 plus. Now what you would expect to happen is the zinc rod to slowly start to dissolve to form zinc 2 plus. But there's a tendency for the copper 2 plus to form copper now. At the moment these are separate. Well, what if we joined our two metal rods via a voltmeter, like so, high resistance voltmeter, and then what if you join the two solutions using something called a salt bridge? Now a salt bridge is filter paper dissolved, that has been saturated with potassium nitrate. So we call it the salt bridge. So what would happen is the zinc rod would start to dissolve to give zinc 2 plus. The electrons would then flow round the circuit through the voltmeter, where the copper 2 plus would gain them to form copper. And by keeping these two processes separate, we've now generated electricity, and what you would see is a voltage showing up on the voltmeter. The purpose of the salt bridge is that it completes the circuit. It allows a current to flow, therefore, but it stops the two solutions from mixing. So it stops the copper 2 plus and the zinc 2 plus solutions from mixing. Practically, what would you actually see? We've already said it, the zinc rod would start to dissolve, whereas the copper rod would start to gain in mass. You'd start to gain copper. So you'd get like an orangey deposit on the copper. So I guess the question at this stage is, what would the voltage be on the voltmeter? Well, you could do the experiment practically and work it out, or you can go to your books of data, or in your case, on the exam paper, you will be supplied with the relevant data and you will be given equations that look like this. So here we've got zinc 2 plus 2 electrons in equilibrium with zinc minus 0.76, that's volts. And then copper 2 plus 2 electrons goes to copper, which is 0.34 volts. Now what do these numbers mean? Well, the more negative the number, the more the equilibrium will lie to the left-hand side, as in the side with the electrons. So because the zinc is more negative, this equilibrium will lie over this direction here, and therefore this becomes the positive electrode and the copper 2 plus will go towards the copper. So we can work out what our feasible reaction is going to be. Basically, the zinc equation is written the wrong way round, because technically what's happening is the zinc solid is going to zinc 2 plus and 2 electrons. And because I've turned this equation around, the minus 0.76 becomes plus 0.76 volts. So the method I follow is that you flip around the half equation that has the more negative or the least positive standard electrode potential and write it out and flip the sign. So now I can kind of get rid of this so it doesn't confuse us anymore. And it shows us what's happening. Copper 2 plus is going to copper and zinc is going to zinc 2 plus. And therefore, to work out what the EMF is, I simply have to combine these two EMF values here, and you get a value of 1.10 volts as your EMF, which means that zinc reacting with copper 2 plus will go to copper and zinc 2 plus. Now, if you asked me what is the EMF for the reverse reaction, so that's copper solid plus zinc 2 plus goes to zinc solid and copper 2 plus. If you ask me what is the EMF of that, well, that is the reverse of this, and therefore the EMF would be minus 1.10 volts. Now, a negative EMF means that the reaction is not feasible as written, so this reaction will not happen, whereas the zinc reacting with copper 2 plus, that will happen because it has a positive EMF value. So the method here is you take your more negative electrode, flip it round, and then it'll show you what the feasible reaction is, and then you can answer the question. So let's take that method and look at another example. The question here is, will chlorine react with potassium bromide? So the method I've shown you is that you take the more negative of the half cells and flip it around. Now these are both positive values, so you go for the value that is the least positive. So this one here, the bromine one, needs to be flipped. So let's do that. 2 Br minuses in equilibrium with Br2 and 2 electrons. And the EMF would be minus 1.07 volts. And then, so we don't confuse things, let's get rid of this. So what this is telling me will happen is that 2 lots of Br minus will react with chlorine, so we're combining the left-hand sides, to give 2 lots of Cl minus and bromine. And the EMF would be these two numbers added together, which would be 1.29 volts. Not 1.29, what am I on about? 0.29 volts, which is positive. And therefore, this reaction is feasible. So the question, will chlorine react with potassium bromide? Yes, it will, because it has an EMF of 0.29 volts and is therefore feasible. In the next question, it says, will dilute acid react with metallic silver? Now, you should be thinking, I know the answer to that. The answer is no, but we need to prove it using the EMF values here. So the equations, we've got 2H plus, which is effectively your dilute acid, aqueous H plus 2 electrons goes to H2, and Ag plus an electron going to Ag, there is 0.8. So we take the more negative or the least positive and flip it around. So that's the hydrogen there in equilibrium with 2 lots of H plus and 2 electrons. That number there still stays at 0.00. So now I flip this around, we can effectively delete this because we've now seen what the feasible reaction is. And the feasible reaction is the combination of these ones, which is hydrogen plus 2 lots of Ag plus. I've times the top equation by 2 to balance the electrons, in equilibrium with 2H plus and Ag. And this reaction, as written, would have an EMF of 0.80 volts. But the question is, will dilute acid, the H plus, react with silver? Well, that's basically saying, will this equilibrium go this way? Well, that would have an EMF of minus 0.80 volts. And therefore, the acid, the H plus, will not react with silver because the EMF is negative. That's what it's getting at. So if you get yourself a book of data, you will find that there are lots and lots of these half equations, and they almost always have the electrons on the left-hand side, and the value for the EMF shown in this column over here on the right-hand side tells you something about the position of equilibrium. So if you look at the very top, you've got potassium in equilibrium with K plus and an electron, and the EMF is minus 2.92 volts. That negative value tells that this equilibrium lies very far over to the left-hand side. We know that potassium is really reactive and wants to lose its electron. That's what the value of minus 2.92 tells you. Whereas if you go right to the bottom, F2 plus 2 electrons goes to 2F minus. You've got an EMF of plus 2.87 volts. The very positive EMF tells you that this equilibrium actually lies over to the right-hand side. The fluorine loves to gain electrons to form 2F minus. So the more positive the EMF, the more the equilibrium lies to the right-hand side, as in the side opposite to the electrons. And the more negative it is, the more it lies on the side with the electrons. And it enables you to do comparisons between different metals. So for instance, it might say which of these two metals is the most reactive, zinc or tin. Use EMFs in your reasoning. Well, the zinc has an EMF of minus 0.76, which means this equilibrium lies over to the left. The tin is minus 0.14 volts, which means it does lie over to the left, but not as much. So the zinc is by far the more reactive compared to the tin. That's what these numbers do. It enables you to compare the position of equilibrium. So we're going to come to the definition in a second. It's taken a long time to get there. But standard electrode potential is the relative ease with which a system can either gain or lose electrons. So we know that potassium loves to lose electrons. Fluorine loves to gain electrons, and it tells you something about that. Now, these are all measured with reference to the standard hydrogen electrode, and we're going to see a little bit about that on the next slide. So when you combine two electrodes, like we saw in the zinc and copper one, they produce an EMF, but all individual EMFs are measured with respect to the standard hydrogen electrode. That was the 0.00 volts, the one that was in the table. So the standard hydrogen electrode looks a bit like the diagram here, where you've got a beaker with hydrochloric acid. The concentration must be 1 mole per dm cubed, says your hydrochloric acid. The temperature is kept at 298 Kelvin, standard temperature. Standard concentration, 1 mole per dm cubed. And then hydrogen gas is introduced at 1 atmosphere, atmospheric pressure. And effectively what's happening here is the equilibrium between the 2H plus and the hydrogen is being generated. And we take that as standard, and all other electrodes are measured with respect to it. And this has an EMF by definition of 0.00 volts. So you've got the H plus ions from the acid in equilibrium with the hydrogen. Obviously you'd have 2 of those and 2 electrons over here. And that is our reference point, and we call that 0. So what I want to do for the last 5 minutes or so is just practice what we've just seen by looking at some exam questions. So this question here says aqueous iron compounds, iron 2 compounds, which means iron 2 plus, form a precipitate of a different colour with aqueous sodium hydroxide. In a test tube, the precipitate can change colour on standing. Use the electrode potential values to explain this change. So the top one is Fe3 plus and Fe2 plus. And then the bottom one is oxygen reacting with H plus ions to form water. So our method that I've shown you is to flip the more negative or the least positive. So that would give you the Fe2 plus in equilibrium with Fe3 plus and an electron, and that would have an EMF of minus 0.77 volts. And then, so as to not confuse things anymore, let's get rid of this one here. So we have iron 2 plus compounds, and they are left exposed to air. Well, if we look at this here, the iron 2 plus will react with the oxygen to form iron 3 plus. And the EMF of this would be plus 0.46 volts. So the identity of our new iron compound is this Fe3 plus, which is aqueous. Okay, one final exam question just to finish off. It says blue oxo-vanadium cations, VO2+, which is these ones here, can be oxidized to yellow oxo-vanadium ions, VO2 which is this one here. Use the standard electrode potentials to identify the main bromine containing product formed when excess of the bromate, let's put that in green, that's this thing here, are added to a solution containing VO2+, which was our one in kind of an orangey colour. So we're starting off by being interested in these two equations here. So we flip the more negative one, which tells me that VO 2 plus will go to VO2 1 plus, which would have an EMF of minus 1.00 volts. Whereas the bromate BrO3 minus goes to the bromide, and that has an EMF of plus 1.44 volts. So stick these two together and you get an EMF of 0.44 volts. So that's the first section, and what effectively has happened is that our bromate has gone to bromide. It's gone this way. And it says that you've got excess of the bromate ions. Well, the bromate ions could react with the bromide, which is now not these two equations, but these two equations. And if you look at these, the more negative is the bromine and bromide. So what happens is your Br minuses, I'm not balancing these by the way, I'm just showing you what happens. The bromide goes to bromine, and the bromate goes to bromide. Now this becomes minus 1.09, and this one here is 1.44. Add these together and you get an EMF of plus 0.35 volts, which means the main identity of the bromine containing product is actually just bromine itself, Br2. Because the bromate will oxidize the bromide to bromine. Well, thank you for taking the time to watch this video. If you found it helpful, please remember to like, subscribe, and keep checking back for more content. Thanks everyone. See you next time.